All right, good afternoon, everyone. I notice I noticed we don't quite have everyone yet. It looks like people are still coming, so let's give them just a couple more minutes and then we can chat. Yeah, just two more people we're waiting on. Great. Ah, there she is. Okay, great. Looks like we're all here now. So welcome back to our second meeting together. And really, before we get into new materials, just I want to check in about materials from lecture 1. But before I do that, I do just want to share with you that all of my lecture recordings will be posted to YouTube for your convenience. So if there was something you didn't catch or you want to review again and hear me talk about it again, you are more than welcome to go to my YouTube channel and check those out. So I'll post them, of course, after our lectures. The actual slides will always be posted beforehand in D2L, but just the actual lecture itself I'll post afterwards on YouTube. So you have access to that. So now, with that being said, that was really the main announcement I wanted to make. What I want to check in with you about is just how the material for lecture 1 felt, any questions you may have, any concerns about the homework, those sort of things, because I don't want to press on if you're struggling with any material from lecture 1, going on to lecture 2. So I'll be quiet and let you either chime in or chat or anything like that if there's anything you'd like me to review from lecture 1 or talk about or what have you.
I had a question about the homework. It was one of the exercises using quota sampling, and I was kind of curious to see like what that would look like when gathering data specifically.
Yeah, so quota is basically what it sounds like. So let's talk about how we might get a quota. Let's say I am looking to test children with autism who've been diagnosed with autism, and I'm looking for 200 children that have been diagnosed with a mild form of autism and 200 children that have been diagnosed with a more severe form of autism. Just for an example, we could choose anything. What I would do is I would, using convenience sampling, right? I would just keep gathering gathering children who have the mild form until I hit 200. Now, even if there's more beyond 200, I would only take like the first 200. Same with the severe form, with the more severe. So I would just keep gathering into my set groups until I had enough, and then I would stop there.
Okay,
That,
thank you.
Yeah, of
Yes.
course.
I have a question about that. If you're unable to get 200, for example, like what would you do?
Yeah, that's a great question. And that's more, practical side of things, right? So what do you do when you set up your N for a certain number and then you realize you can't get there? And this comes up a lot in practical research. So what people often do is what's called, I don't know if you've heard of power analysis yet, but it's what tells you, you know, do I have enough participants to reasonably conclude that what I find in my sample will generalize to my population. So specifically, do I have enough power to detect a finding, a difference, an association, whatever I'm looking for? Do I have enough people to detect that? And what people will do is they'll do a post hoc analysis or an after analysis um, after the fact to say, okay, maybe I didn't have the power I wanted to, but I got enough to reasonably show this. So that's one thing that people do. So they'll try and justify, even if I didn't get my 200 and my 200, hopefully I still have enough to still conduct my analysis. The other thing people might do is drop back to a different kind of analysis that's more lenient. That how do I say this? It doesn't require the same amount of power, It doesn't. Some more complicated analyses require more power than simpler analyses. So what you're trying to do is get enough people to show, and usually the gold standard is 80%. So 80% of the time, if there is a real, and we'll just say difference here, if there's a real difference, I'll find it 80% of the time. That sounds pretty crappy to my ear. It sounds pretty crappy to most people's ears, because you'd really rather have that be up by like 90% or 95%. But that requires so many more subjects, that so many more participants, that we settle to 80%. And sometimes people even settle for 60% or 50%, because they can't get the amount of participants they need. So it is a sacrifice when you don't get the number of participants you need to power to finding the result you're looking for. And there's some different ways to cope with that, like I said. But of course, it's just not ideal. Does that help? Okay, great. What else? Try and put you at least for a minute or two like this so I can see you all. Okay, that's a little better. I can see most of you. Maybe if I do that, I can see all of you. Okay, great. Um, so how do does the lecture one materials, did they seem to go over okay? Or is there more a case of, I have some questions, but I'm not sure how to pose them. So if you feel like you have a question, but you're not sure how to pose it, like if there was some confusion about lecture one, maybe you can just tell me the area or topic. If not, that's fine, and we'll move on to lecture two.
I don't think I have any specific questions. I think I just need to um, like practice. So we talked about, like, for example, went over the ANOVA test, the MANOVA test, is pretty much like the basics of those, and the other 15 or so that you went over.
Yeah.
Practice.
We'll be doing those throughout the whole semester. So if that part didn't sound clear, don't worry, because we're going to get back to the ANOVA test, back to all those other tests. So that's good. That's not a problem. Okay, so if something comes up, let me know. Either if it comes up during lecture, let me know. If it comes up afterwards, then you can always email me, set up an office hour time, whatever you like. Okay, so with that being said, let's then press on to lecture two. So I'm just going to put this in slideshow format so you can kind of see it that way. So the next homework assignment is homework homework 2, of course, and it's a chapter 1 practice exercise that I have. It's chapter 1 from a different book, but I've posted it for you under homework on D2L. Okay, so you'll see it posted under homework 2. It's a PDF, and once again, we're not going to do number 1. I'm going to have you work on 2 through 10. And if you we'll do the same game that we're going to do this time. So during our break, I'll pull up a random number thing so we can actually choose one from last time. And then we'll do the same thing for this one. So 2 through 10. And then I was thinking, just to help you guys out, if you'd like, I'll post the answer for exercise 1 up on D2L. So I'll do that for you guys. I'll post just so you get a handle on what they're looking for these different ones, because sometimes it's a little bit hard to know with the phrasing and everything. So I'll post the answer for, I might be about to be interrupted. I apologize if I am. We're adapting to a new schedule here. I'll post number 1, work on 2 through 10, and let me know if you have any issues. And then, of course, that'll be due next Wednesday by 4:25 p.m., just like it was this week. Okay? If any questions about that, like I said, just chat in or let me know. Okay. So where I want to pick up then is where we left off with frequency distributions. Okay, and if you remember, we talked a little bit about what a frequency is, what a frequency distribution looks like, what a histogram looks like, those sort of things. So now let's talk about some different kinds of frequency distributions. And basically what we're looking for is the pattern of frequencies over the various values, or how the frequencies are spread out. Okay, so for example, and you're typically, when you think about these, think about histograms, think about those connected bar charts that would show you a picture of these things. And I will show you some pictures along with these descriptions. Unimodal is a histogram with one very high area. So the normal curve is a unimodal distribution, right? Because it has, can I do this online? Kind of. It has one high area in the curve. Bimodal, 2 high areas. Multimodal is 2 or more high areas. So a bimodal distribution becomes one type of multimodal, because if you have 2, you could call it bimodal, because that's 2, or you could call it multimodal, which is 2 or more. If you have 3 high points, you have to call it multimodal, same for 4, same for 5, etc. But if it's 2, it could be called either bimodal or multimodal. Okay. And then a rectangular distribution is when all values have approximately the same frequency. So in other words, a good example of a rectangular distribution is if I had a fair die with 6 sides on it, and I just kept throwing it again and again and again, let's say 1,000 times, then what you might anticipate is that I would pretty much at the end wind up with an equal number of 1s, 2s, 3s, 4s, 5s, and 6s, right? That would be rectangular. Okay. So let's look at some pictures of these. Here is a unimodal on the top, an approximate bimodal beneath, and an approximate rectangular on the bottom. Okay. So I like these drawings just because they're not perfect, and when you collect data, nothing's ever perfect. So I mean, I've seen some really very nice, beautiful data before, but usually not perfect. So this is a more realistic look at some of these distributions. Okay. So hopefully you can see the 1 point for the unimodal, 2 points for the bimodal, and the relatively rectangular distribution here. All right. So if you roll 2 die at the same time, and they're both fair and they both go from 1 to 6. I don't know if any of you are familiar with dice rolls and those sort of things, but then there would be a very common number there, and that's 7, because you can get to 7 the most ways. by 1 and 6, 6 and 1, 2 and 5, 5 and 2, 3 and 4, 4 and 3, right? That's all different ways to get the 7 with 2 die. So because it's the most common, you would wind up with 7 near the top here, and then you'd have 6 and 8, etc., etc., until you get out here to 2, excuse me, and 12. Okay. Now, speaking of perfection, there we have our perfect normal curve for you. And it is a unimodal curve, as I mentioned before. It's got that old-fashioned bell shape, right? And it's symmetrical, which means if I took it and folded it in half, both sides would line up. So that's our normal curve. Now, remember, these are all frequency distributions. So a lot of times what we're assuming is that our variable has a normal distribution. And that gives us the power to run all of the parametric statistics, or at least some of the parametric statistics that I talked about last week. It gives you the power to run parametric versus non-parametric statistics when you have a normal curve. Okay, and specifically, I'm most likely talking about your, in most cases, I'm talking about your dependent variable, but we'll talk a little bit more about that as we go forward. Okay. So the normal curve is bell-shaped, unimodal, and symmetrical, as we just talked about. Things that fall out with a normal curve are people's heights, although you tend to get different height distributions for different genders, but still it works out to be pretty normal. Test scores, as you've probably heard about, grades, IQ scores, and even sizes of snowflakes all have a normal curve distribution. So what's the point of that? The point is that it occurs pretty frequently in nature, and I think it's why we got started down this whole normal curve path and hope that everything that we'd ever measure would have this normal curve distribution. And that's how we came up with all these. And we'll talk more about it, what we mean by parametric tests, but it includes things like the t-test and the ANOVA and linear regression. All those kind of things are parametric tests. All the typical tests you've heard of are parametric tests. But they all assume the normal curve. Okay. Variability. So we kind of leapt into frequencies when we first talked about this notion that central tendency isn't enough, right? You can't simply talk about mean, median, and mode and call it a day. It's not enough information. So we needed to understand how things are spread out. That's why we started talking about frequencies and frequency distributions. And now we're going to talk even more specifically about variability, how spread out the scores are in a distribution, or the amount of spread of the scores around the mean. Okay. So here's a good example for you. Let's talk about housing prices for just a moment. And if you look at both graphs, okay, you will see that they have the same average. They have the same mean. Okay, if we just look down the center here, this is the same mean housing price. But in the top figure, the housing prices are much more consistent. They're much more narrow, right? So housing prices here have a smaller range, and they all tend to kind of lie in this small range. Whereas housing prices on the bottom graph are much more spread out, a much wider range, less consistency. So this bottom picture would have a lot more variability than this top one. Okay. Okay. So when we're talking about variability, one thing to remember is that the mean and the variability are different beasts. One does not tell you anything about the other. Okay, they're separate things. So in other words, let's look at this picture. We got the blue and red, or whatever colors you want to call these. But you can see that even though the blue and red have the same mean, which is coming in the center here, the center of our distribution tends to be the mean of our distribution, especially when it's a beautiful normal curve like, well, close to a normal curve like this one, then our mean tends to be right at the center. So they both have the same mean, but you can see that this blue-purple one has a much smaller range, is a lot less spread out than this red one. So same means, different variability. Okay, next one. Different means, right? Mean over here for the blue, mean over here for the red, but same variability. In other words, if I picked up the red and shifted it left to be onto the blue one, you'd see they'd pretty much line up, right? Because they have the same spread or same variability. So mean and variability are different things. Okay. Okay, so since we're talking about spread, let's talk about the minimum, which is our lowest number in a set of numbers, in this case 19. Our maximum, which is the highest number in a set of numbers, which in this case is 31. And that brings us to this notion that maximum, minimum, bigger is not necessarily better, right? A high bowling score is good, but a low golf score is good. And a high or low phone number is neither good nor bad. But what this leads to is the range. And the range, of course, is our maximum minus our minimum. Our maximum minus our minimum. So 31, our max, minus 19, our min, is 12. Okay. So when you're getting descriptive statistics for your data and you're using SPSS, something that you might want to get off the bat is your min, max, and range. They're really helpful pieces of information. I know they're kind of basic, but it would tell you, for example, if you had any crazy outlying data, you know, by looking at the min and max, by looking at your range. So it is helpful descriptives. Okay. And then I ask you to consider the following two sets of quiz scores for 9 students. Now, you can consider which has the greater range and which one has the greater variation. So again, if we subtract the high score minus the low score, 10 minus 1 gives us 9. 10 minus 2 gives us 8. So this technically has the larger range, right? 9. So, but this one, if I look at it, I would argue that this one has more variability, right? Because this one, almost everyone got a 10. This one's much more spread out. Okay. So it's not, there's something more than just range that we're getting to here. And one of the big statistics you're going to encounter a lot, and I'm sure you probably have in research articles to date encountered this, is the standard deviation. Okay, and it's a great way to indicate how much diversity there is within a variable. It's the most used method for indicating variability. So scores that are grouped closely around the mean produce a lower standard deviation. Scores that deviate more from the mean produce a higher standard deviation. And remember, M, X bar are your typical symbols for the sample mean. Okay. All right. I'm so used to pausing to get questions from you guys, but it's harder to do that kind of in this scenario. So I'm just going to ask you to just pipe in if you have a question. And if I need to have you wait a second, I'll wait. Especially if you pipe in via chat, I can do that easily. Okay, so let's look at standard deviation for group A. And you can see they're all very similar height, Here's their mean height. And their standard deviation is 0.577, which is, you know, pretty low number here. We'll talk about what standard deviations mean and what big and small numbers are in a little bit. Here is group B, and you can see while they have the same mean, their standard deviation is much larger. It's 20.744, and you can see there's much more diversity in the heights. Okay? All right. So what is variance then? Because you'll see variance come up as another statistic out there. Sometimes people will report it. And it's just taking the standard deviation and squaring it. Okay, so just SD times SD gives you variance. So if you look at these three numbers, 86, 45, 71, your standard deviation is 20.774. And so you would square that to get 431.559. That would be your variance. All right. So I want to show you the symbols that you might encounter for variance and standard deviation in journal articles and what have you. And these are them. So if we're talking about variance in, excuse me, I missed one. Variance in the population, it's sigma squared. Standard deviation in the population is simply sigma. Right? Because what did we say? We take our standard deviation, sigma, square it, sigma squared, to get variance. Now, on the other hand, we have our sample standard deviation, which is S. We square it, oops, sorry. We square it to S squared to get our sample variance. Now, I have already used the term sigma twice at this point. Will this let me just write on here? One was the symbol for the mean that looked like the E, and one is this guy over here, sigma, that looks like the O with the hat. And unfortunately, one is in Greek, one is uppercase, one's lowercase, and that's why they both have the name sigma, even though they mean very different things. Like I said, in this case, sigma, standard deviation. With the weird looking E, it means add them up or sum them up, summation. Okay, I can I'm going to try a brief experiment here by sharing to my whiteboard and seeing if it will let me type on here. So I can just show you real quick. I want to draw, I guess freehand. That's a really bad sigma. I apologize. That's kind of what I can do with my mouse. But hopefully that looks familiar. I can try again. Maybe if I try a straight line, that'll go better. No, it won't let me do multiple lines then. Okay, never mind. Hopefully that at least reminds you of what the sigma actually looks like. If not, like I said, chat in, and I will, of course, go back to a slide that actually has it proper. Okay, and now we're back here. Lovely. Okay. Okay, so let's look at this slide right here. Okay, so we'll try that one more time. Slideshow from the current slide. Why aren't you cooperating? Oh. There we go. Okay, so the next thing I want to show you is N. We did talk about N last time. We talked about capital N, lowercase n, and we talked about that for the most part. Uppercase N means population, and lowercase n refers to the sample. There will be an exception to that rule that we'll talk about much later. And basically what we're talking about is how many elements do you have in your data set? Typically, how many numbers do you have in your data set? Okay, so that's an important piece. Here, as you can see, we have 10 numbers, hence n equals 10. Okay, so now we're going to kind of hopefully dive a little bit deeper now, talk a little bit more about normal distributions and z-scores, and then get into some theoretical concepts. Okay, so remember, standard deviation is the average amount the values of scores differ from the mean. Here's our normal curve. Here's our coin flips that we talked about last time. Right? I'm showing you 3 different things for a reason, because now we're going to put all these together. Okay, now we're going to put normal distribution and standard deviation together. Okay, so here's what I want to show you. If you have a normal curve, and this is why people love the normal curve, and you go from the mean to 1 standard deviation up, it always captures 34% of the people, of the items, of whatever's in your data. If you go from the mean to 1 standard deviation down, or -1 SD, you will also capture, because this is a symmetrical distribution, you will also capture 34%. And these numbers are approximate, I should tell you. For example, between 1 SD and 2 SD, it says 14%. I think the number is closer to 13.77, but 14% I think is a good thing to hang our hat on. Same with 1 to 2 going in the negative direction, 14% of people. And going higher than 2, you get 2%. Going lower than 2, you get 2%. So from the mean up, we get 50%. From the mean down, we get 50%. Okay. So another way you may have seen this in the past is called the 68, 34 and 34, 68. That's 1 standard deviation up or down. 95, which if you add these numbers, you get something close to 95 between -2 and +2. 99.7 rule, which I'm going to show you right now. So we've got 68% between 1 standard deviation down and 1 standard deviation up. 95% between 2 standard deviations down and 2 standard deviations up. And 99.7% between 3 standard deviations down and 3 standard deviations up. And these numbers always remain the same if you're working with a normal curve. By the way, notice down here the symbols, they're all population symbols, right? Because right now we're working, for the moment, we're working in the perfect world of populations and normal curves. Okay. So, falling out here, beyond 3 standard deviations, either on the plus side or minus side, would be pretty rare, right? Only 0.3% of the population do that, which if we divide by 2, only 0.15% here, only 0.15% here fall outside of that. Okay. So save this for Valentine's Day, and you can tell your significant other that you're 3 standard deviations above the norm. Okay. Z-scores. Let's talk about Z-scores. Z-scores are standardized scores such that your mean will be 0 and your standard deviation will be 1. What this does is it allows for the direct comparison for different variables. And I'll explain what we mean by that in just a moment. A z-score is the number of standard deviations a value is above or below the mean of the scores in a distribution. So in other words, let's say one person took a test, and let's say you're working with different cognition tests, okay? And one of them has a mean of 100 and a standard deviation of 15, like like a standard IQ test, right? But let's say the other has a mean of 60 and a standard deviation of 7. And then on the one test, someone gets 120, and on the other test, someone gets a 72, and you want to compare the two. Z-scores, if you convert them to Z-scores, you can actually compare the two quite easily. So that's the power of Z-scores. And you can convert from a raw score to a Z-score or vice versa. Okay. Any questions you want to ask so far? Again, put them in the chat and I'm happy to answer. Okay, because now we're moving into a little bit more about inferential statistics and hypothesis testing. Okay. So we're getting a little deeper with each little section here. Yes, and I'm always excited that we're doing inferential statistics. Okay, now this is the branch of statistics devoted to drawing conclusions or making inferences about populations based on sample data. Okay, so we're always interested in our sample data. Remember, we collect our sample data, and then we want to draw a conclusion about our population. And we always have to look at our sample and be thoughtful about, okay, so what's the appropriate population to which I can draw a conclusion? Okay. Now, hypothesis testing is a systematic procedure for deciding whether the results of a research study support a hypothesis. An hypothesis is simply a prediction about the outcome of a research study, right? So what we're basically saying here is that we're going to have these steps that we're going to take to show whether or not we can reject or not reject our null hypothesis. That's what we're going to get to. Okay. Before we get there, let's talk a little bit about independent and dependent variables. Now, historically, this is one that I've known people have struggled with. So let's take a pause here and talk about it real quick. The independent variable is the variable that's manipulated or chosen for study. Whereas the dependent variable is a variable that is measured or observed in a study. I like to think of the dependent variable as my outcome variable. And then I think it's easier sometimes to figure out your outcome variable first, label it as dependent, and then work backwards to your independent variable. Okay. So let's look at an example together. Okay. Now, most important part here is I want to know if you get the reference.
I love Lucy.
Yeah, it is. It's I Love Lucy. Great. Yeah, that's absolutely right. Yeah. So, okay. So now let's look at it and let's identify variables. Okay. So a sample of persons who happen to try out the new multivitamin Vitamin, which is designed to boost energy levels by taking it daily for the past 6 months are selected. Energy levels for the Vitamin group is compared to the known population energy level at the end of 6 months. Okay, so what's our outcome variable? What's our dependent variable here? What are we measuring?
Energy levels.
Yeah, it's energy levels. That's absolutely right. Our dependent variable is energy levels here, because that's the outcome. That's what we're looking at the end. So our independent variable is, what else is in here that's varying?
The condition of if you're taking the vitamin or not.
Yeah, whether or not you're taking the vitamin. So yeah, absolutely right. So and multivitamin use and energy levels. Okay, so perfect. So this again, I'm going to show you now another example, and you'll notice just a small change in it. The IV and DV are going to remain the same, but there's a small change in how I did this study or how the study was conducted. A random sample of persons are selected to take the new multivitamin daily for 6 months. Energy levels for the Vitamin group are compared to the known population energy level at the end of 6 months. Okay, so I think you can see the difference here, right? Here I took a sample of persons who happened to try out the new multivitamin. Here it's a random sample of persons who are selected to take the new multivitamin. Which study, and I'll just show you, it's the same IV and DV. Which study you like better? Which one seems stronger to you? Yep, number 2. Yep. It is number 2, and it's of course because you took that random sample of persons, right? That makes it stronger. And what I'm getting to here is that when you control that IV, when you control who gets which condition in a study, that gives you, it's a much stronger study. Now that doesn't mean we don't study things that we can't control the IV for, or they're not important to study, or anything like that. It just means when you can, if you have the option to control the IV, it's really helpful to do so. And it can get you on the path to causality. Now, if we can't control the IV, I mean, and I'll give you an easy example. Let's say you're doing a study among first care first care responders or emergency care responders in a natural disaster, and those who are living close to the natural disaster who are not those emergency responders, right? So I can't control who's an emergency responder and who's not. But that doesn't mean I don't want to study this. Of course I want to study it. It's a very useful study to look at their post-traumatic stress outcomes or what have you. But it does mean I'm not on the path to causality. Like I can't show cause. So if I find that first responders actually had greater levels of post-traumatic stress symptoms 1 month out as compared to those who lived close to the natural disaster but were not first responders, I couldn't say, so being a first responder causes you to have higher levels of post-traumatic stress in this situation. I can say there's an association, that there's a relationship that we're looking at here, but I wouldn't talk about causality. Now, even here, there's a lot more conditions you have to satisfy to get to causality. And maybe this is all old hat to you, I don't know. But there's a lot more conditions, but at least you're on the path to causality here. Okay. So, whoever it was who knew the Lucy, would you, we need a brief, like, kind of half break here. So would you share the Lucy example if you know it?
I can try. So I think she's filming an advertisement for this new vitamin regimen, and she keeps drinking it and like says or whatever after it, but she keeps messing up saying vitamin regimen or something in the script, so she has to keep taking it, and she comes out like she kind of gets drunk.
Yeah, apparently the vitamin regimen had a high level of alcohol in it, and it doesn't taste good either. So she's like, it's delicious, or whatever, and it doesn't come out right. So anyhow, so that's the story behind the example I gave here. Anyhow, let's move on. Okay. So we talked about which study is more convincing and why. And this is what I was sharing with you just a moment ago, that when we have manipulation of the IV, when it's manipulated by the researcher, we are on the road to causation. When it's simply chosen for observation, still a very important study, still talk about relationships and associations, but you're not on the road to causation. Okay. Okay, so causation. When you want to determine the causes of behavior, first thing you need is temporal precedence, which means you have to show that the cause happens before the outcome. Okay. Next, you have to show covariation of the cause and effect. This means if the cause occurs, the effect occurs. And just as importantly, if the cause does not occur, the effect does not occur. So sometimes people get the first part of that right and kind of forget about the second part, that if you have the effect occurring with no cause, you can't show causality. And finally, and of course this is the toughest one, you have to rule out alternative explanations. So if I did that, let's see, if I did a study where I assigned people to be emergency responders that worked within a mile of a particular natural disaster, and then I assigned other people to be an emergency responder. I see a question coming up, I'll get to it in just a sec. Emergency responder that worked 10 miles away from the area. And I wanted to, at some point, evaluate, let's just pretend I'm doing this well, I've got the causation, I got my temporal precedence, I got my covariation of cause and effect, and I showed that there was more post-traumatic symptoms in those working closer to the event. Well, something maybe I didn't account for is sleep, right? Maybe those working closer to the event are not sleeping as much, and that is increasing symptomatology. We don't know. So there's so many alternative explanations that we can sometimes think about related to this. And can I explain temporal precedence again? Absolutely. Temporal precedence, cause must happen before the effect. So in this case, we might want to look at post-traumatic stress levels in all of our first responders before they actually started working this event, and then look at their post-traumatic stress afterwards, right? So we want to make sure that it wasn't already there, that the cause happened working this event before the effect of post-traumatic stress symptoms. Okay. All right, so that's just some basics about causation there to just give you an idea for it. Click back in here. Okay, so now let's talk a little bit more about hypothesis testing. So this is probably a concept you've heard a little bit about, or heard maybe a lot about, null hypothesis and alternative hypothesis, right? So what's the null hypothesis? It's saying that there's no effect, no significant difference, no relationship. Whereas the alternative hypothesis, which is H1 as compared to the H0 or H0, there is an effect, there is a significant difference, there is a relationship. So having said that, I'd like to talk about how I'd like you to phrase null and alternative hypotheses. That I think this is a helpful way that you don't get into trouble when you're trying to phrase these. Okay, so by the way, the evil smiley face up here is indicating that yes, we are rooting as researchers for the alternative hypothesis. That is the researcher hypothesis. That's what we're hoping is true. Now, you might ask the question, and this is asked, well, what if I want to show that there is no significant difference between groups? That's a toughie. There is that kind of equality testing or equivalence testing out there. There is a way to do it. It's a little bit of a challenge. So in our field, we generally try to stick to the null hypothesis, alternative hypothesis being the researcher hypothesis scheme. Of course, if you have a dissertation topic that you're thinking of that doesn't meet this scheme and you're concerned, please feel free to come talk to me about it. There might be a way to either tweak it or to work around those things. Anyhow, so that's your null and alternative. Okay. So let me show you null and alternative for our vitamin D regimen. And let's start with the alternative. That's how I usually recommend people start. Start with the alternative and just think through, what is the research or hypothesis? What are we trying to show? So what we want to show in this case is that those taking vitamin A vegemin do have significantly higher energy levels compared to the population. Now the null, what I've written here is those taking vitamin A vegemin do not have significantly higher energy levels compared to the population. So here's the question. Why do I not say for my null, those taking vitamin A vegemin have significantly lower energy levels compared to the population? Why would that be not such a great null hypothesis?
Is it because you're comparing it to like the normal level of energy and you're not trying to prove that people have low energy without it?
Right. I think you're right on there. So when we talk about the null and alternative hypotheses, we want to cover the whole universe of options, right? So if we said have higher, have lower, to your point, we're not covering what if it's the same. And we need to cover that. So this null and alternative has to equal all the possible things that can happen. So the easiest way, in my opinion, to form an alternative and null hypothesis is to, like I said, first form the alternative, figure out what you're trying to show, and then just add the word not to it. I mean, I know it sounds simple, but it is simple and it works. That way you don't get tripped up in language and find yourself leaving out a possibility that you didn't mean to leave out. Okay? All right. So that's my recommendation there. Okay. So what else about a study makes it more convincing? So if I told you that this multivitamin study, and we'll take the second one that we like better, our random sample, contained 10 people, or if I told you that it contained 10,000 people, I'm guessing you'd like the second study better, right? So sample size. Sample size will make a study more convincing. The bigger the sample we have, the better position we are, and we kind of talked about this a little bit before, but the better position we are in to show that there is a difference, that there is a finding here. So sample size is important. Effect size. Effect size is very important too. So if I told you that those taking vitamin A vegemin had an increase in energy levels of a quarter of a standard deviation. Right? It's not very exciting. But if I told you they had an increase of 2.5 standard deviations, suddenly that's a lot more interesting. So effect size is also really important. What kind of effect did we show? How big an effect did we show? And as I mentioned before, sample size, big contributor to power, big contributor to this notion of how easily or with what % likelihood can we show that there is an effect if there really is one. Okay, so even if there is an effect, how likely is it that I can show it? And the gold standard is 80%. 80% of the time, if we have a finding, we'll show that it's actually there. And like I said before, it does not sound like a great gold standard, but there it is. In fact, I remember when I was teaching this class that people were saying, I'm going to have a 95% power because I really want to do that and I really want it to be a great study. But then when it comes down to it and you're looking at your actual ends and the statistic that you're supposed to run, sometimes you back off of that. But hey, I mean, it's always better if you can to make it more powerful. Another question that sometimes comes up is, can you overpower a study? Can you have so many people in a study that like everything comes out significant? Every test you run comes out significant? It can happen when you get into the millions. I've been on one study that was like that we had to like kind of adjust for that problem. But for the most part, you're in psychology and the behavioral sciences, you don't run into that. We're typically struggling for more power, not less. But it's possible. Okay. So here's our normal curve again. Remember we looked at this just a little bit ago. And what I want to share with you now is cutoffs for the normal curve. Okay. So let me put all this in here. Let me back off to that point. Okay, so let's look at it this way. What we wanted to show typically is that our finding is in the top 5% of the population normal curve if we're comparing to a population. So in other words, remember when we were looking at standard deviations not long ago? So I'm showing you that this is the z-score of 0 or 0 standard deviations with a mean. 1 standard deviation up, 2 standard deviations up. Well, if you actually go 1.64 standard deviations up, that's the cutoff for 5% in your tail. And if you've ever seen alpha equals 0.05 or p less than 0.05, this is the concept we're getting to right now. So in other words, let me bring vitamin Vegemin back. This is this black bar. I wish I could get rid of it. Okay. Sorry. Okay, here's vitamin Vegemin. Okay, so remember we had people taking vitamin Vegemin, right? And we're comparing them to the population. Okay, so if the mean of vitamin Vegemin is just to the right or as far right as you like of this line, you want it to be to the right of 1.64, then you'll be able to reject the null that there was that said that you do not get higher results with vitamin Vegemin. Okay, let me give that to you one more time. So if you land up here in the gray shaded area with your mean of vitamin Vegemin, you get to reject the null. You get to reject this notion that there's no finding. And what was our null in this case? That those taking vitamin Vegemin do not have higher energy levels. That's the concept we get to reject. Because indeed, they do have higher energy levels. It's just a weird language, right? In our field, we talk about rejection and not rejection. And I know in general psychology is a very accepting field, but in this case, it's all about the rejection, okay? Reject, do not reject. And we're always talking about the null. So we're always going to make this choice. I'm either going to reject my null or not reject my null. Now you may see different language around this. I have seen retain the null. I don't like it as much. I think it's far easier to talk about either reject or do not reject the null. And we are always trying to reject the null. That's our goal. Okay, so this is how this one works. Okay, let's say, just for fun, that we had said that those taking, I actually, did some research about vitamin Vegemin. I found it's actually very dangerous and that it'll lower energy levels, okay? So now my hypothesis is vitamin Vegemin will lower energy levels. Then we'd want to look at it this way. All we're doing is looking at the opposite side of the curve. Now, if we're down here in the bottom 5%, we're going to reject the null. And if we're anywhere else, we're not going to reject. Now, that's a one-tailed hypothesis or a directional hypothesis that I was just sharing with you. Now, that's when you decide a priori this is going to be higher or this is going to be lower. Now, here's the downside of making a one-tailed prediction. So we'll stick with this lower side, right? So I made the prediction that vitamin regimen is dangerous. It's going to lower energy level. Let's say, just for fun, that those with vitamin regimen came out with a mean all the way out here. Do you see? Hopefully you see my cursor. And thank you for shaking your head. Let me know that you do. And it was all the way out here, all the way in that right side tail. You can't reject the null because you predicted it was going to be low and it came out high. So you got to match your prediction. You've got to match your prediction. If you said high, it's got to come out high. If you said low, it's got to come out low. Now, let's say you don't like this scheme. That's okay. I have a solution for you, and it's called a two-tailed test or a non-directional test. Now, this is great. Now I gave you gray on both sides, right? So if you fall up here in this range, you get to reject. If you fall down here in this range, you get to reject. If you fall in the middle is the only place you don't get to reject. Now you probably are thinking, I bet there's a cost for this, and you're right, there is a cost for this. The cost is now, as opposed to hitting that 1.64 or negative 1.64 mark, now you got to get up to 1.96, beyond 1.96 or lower than negative 1.96. That's your cost. Because now, why is that? We're trying to keep our alpha to 0.05, and you may even decide to have a lower alpha. We generally don't go higher than 0.05, but you could go lower, right? You've seen p-values where they say less than 0.01, less than 0.001, what have you. So you could play it real conservative and set your alpha lower if you wanted to, but generally we set it at 0.05. That's a very typical convention. Well, we got to retain that 5% then in our tail. And the way to do that is to split it in half, to put 2.5% here, 2.5% here. That's why these numbers are 1.96 and negative 1.96. Because now we've gone all the way out to putting 2.5% in our upper tail and lower tail. And I'm going to the chat because I see there's something that's come in here. Oh, yeah. How would we word the hypothesis for two-tailed? Great question. So yeah, the way you would do that for our vitamin regimen example is you would say that those taking vitamin regimen would have different level of energy than those not taking vitamin regimen. And then the null becomes those taking vitamin regimen would not have a different level of energy than those not taking vitamin regimen. Also, you suggested higher or lower. That would work too. I mean, I like using different, but you can use higher or lower. Okay. So that's our one-tailed and two-tailed test. Okay. So here's the thing. You take all this time, you do all this research, you're working on a dissertation, you make your conclusion, And you want to know if you're correct or not, right? And here's the thing about statistics, you never truly know. Because I am magically showing you right now in this picture what the population looks like. As a general rule, now in some cases maybe you know kind of what the population looks like with IQ scores, but as a general rule you don't. You only know what your sample looks like. So if your sample, so here was our population for no vitamin D regimen, right? Here's our little sample, right? Because we only took about 200 people, we'll say, who took vitamin D regimen. And here's the result. Here's what the sample looked like on the energy level scores. So if I cut through to the mean, looks pretty high. Great. So hopefully when I generalize back to my population, what I am saying is, that was supposed to be more dramatic. What I am saying is my population looks like that. Great. If it does, that's wonderful. Everything worked out great. But I don't know for sure that my population actually looked like this. In fact, I'm going to skip ahead one. Here's the same graph, right? Same picture setup. What if my population actually looked like that? And I got a biased sample. I'll never know. All I see is this. I don't see this part. So it could look like this, or it could look like this. I don't know which one, and I won't know which one at the end of my study. So there's always a chance. There's always a chance that I get it right or I get it wrong when I reach the decision, as I would here, to reject the null, right? Because again, just looking at this, I'm pretty high up. I've got a really high energy level amongst my vitamin D regimen folks. So I'm going to reject my null. Okay. Let's go on to another scenario. Now, this is my sample of vitamin D regimen folks. Well, to me, the mean looks very similar to my folks who did not take vitamin D regimen. So I'm not going to reject the null. And again, if this is what the population actually looks like, if my sample and population look the same, then great, I made a correct decision in not rejecting my null. However, if it looks like this, and I'm going to skip ahead again to D, then in fact, I made an incorrect decision because look at my population. Look how high their mean is. It just is that I happen to get a biased sample. Okay. So let me tie this all together for you into this table. Sorry, 1 second. I'm teaching right now, Chris. Go ahead. Go ahead. Sorry about that. We're adjusting to our schedules here. Okay, so this is the table I wanted to show you. Okay, so In the real world, in the true state of the world that we do not know, this is what we'd love to know, but we don't know. Either the null hypothesis is not true and there's an effect, or the null hypothesis is true and there's no effect. So that's our true state of the world, the real situation that we don't know. We get to make a decision at the end of our study. The decision will be I reject my null or I do not reject my null. Excuse me. I either reject my null or do not reject my null. Okay. So if there's a real effect, right? There was a difference. There was something important going on. I found that difference. I rejected my null. I made a correct decision. That's called power. If, on the other hand, I do not reject my null and there was a real effect that exists, I missed it. There was a real difference, but I didn't see it. I didn't see it in my data. Who knows why, but I didn't see it. That's called a type 2 error, and it's 1 minus power. Okay, so this is all if an effect exists. So if an effect exists, like we were talking about, there's only two possible things that can happen, right? I either reject or don't reject. So this is the land where an effect exists. I either reject or don't reject. I either make a correct decision or have a type 2 error. So these two possibilities have to add to 100%. Because this is the true state of the world. Okay. By the way, the A and D here relate to the pictures I was showing you before. So if you're curious where those come in, that's the only reason for that. So my type 2 error, often also called a false negative, is what we were just talking about. Okay, now let's change gears and say that there's no effect. There's no effect, no difference, no whatever. And I do not reject the null. Then I made a correct decision. That's 1 minus alpha. The last case is the one we're really trying to avoid. It's when there's the null hypothesis is true, there's no effect, but I reject the null. In other words, there's no effect, and I say, I found an effect. That's type 1 error. That's a false positive. That's alpha. That's what we try to avoid at all cost. You do not want false positives in psychology. Now, in other fields, it may be different. For example, in a medical field, I can give you a pertinent example. If you're testing for COVID-19, for example, right, then false positive isn't great, but you can have the person come back and take a more sensitive test. In that scenario, you really don't want the false negative. You don't want to send someone away and say they're fine when they're not fine. Right? So that's a scenario in medicine where it's different, but in psychology, I'm telling you, it's this alpha we really want to control. And that's why we tend to set our alpha so low. If you notice, our false positive error, alpha, is set down to 5% or 0.05. That's what we kept doing, or even lower sometimes people want to go. Whereas our power, if our power was set to 80%, then our type 2 error becomes 20%, right? And that's a lot higher than 5%. So we're really controlling for this one. Okay. I think I'm hoping I included this one other. Yes, I did. Okay. So let me give you one more example just in case this isn't sitting nicely. Let's say we're in a courtroom now and the person is either guilty or innocent. Okay. And that's the true state of the world. Now you are a juror trying to figure out whether they're innocent or guilty. You will never know for sure. You're taking a guess. And so your choice is to either convict or to not convict. So if the person is guilty and you convict them, great, you made a correct decision. If they're guilty and you do not convict them, a false negative, well, they kind of got away with it. If, on the other hand, they're innocent and you do not convict, you made a correct decision. But if this is the one we're trying to avoid, we don't want to convict the innocent. So if they're innocent, we convict them. That's the error in our field that we're trying to avoid. Okay. Let's pause here, take a little break. Let's come back in about 10 minutes and talk more about power, the distribution of means, and confidence intervals. Feel free to chat in the meantime if you have any questions, and I'll see you back in 10. I stopped the recording when we took our break and I forgot to restart it. So glad you're all here. I'll try and remember to do that going forward, but thanks for the note on that. Okay. Okay, so that's our either bigger mean differences or smaller standard deviations will get you bigger effect size. Okay. All right. So far, we have talked about population and sample distributions. But I want you to know about one more sampling distribution, and that's the sampling distribution of means. That's another type of probability distribution. So here's how this works. We obtain multiple samples, all with the same sample size n, and plot the mean for each sample on a frequency distribution. Okay, so let me give you, the coin flips was actually an example, but I am going to skip ahead to this IQ example because I like it better. Okay, so let's look at this example here. You have a population of IQ scores of 10-year-olds. Okay, so just imagine you have this large vat of IQ scores for 10-year-olds, and they can maybe be written on little slips of paper that are in this huge bowl, okay? And you know that the mean for the population is 100, and the standard deviation for these IQ scores is 16. Okay. Now, you're going to reach into the huge bowl and pull 64 slips of paper, or 64 IQs. You don't care about the individual slips of paper. All you're interested in is their mean. So you take the mean, you take the average of these 64 slips of paper, and you get 103.7. Throw those pieces of paper away. Reach back in the bowl. Get another 64 slips of paper. Again, you don't care what the individual slips say, you only care about their average, so you take the average of the 64 numbers, and this time you get 98.58. Throw those away. Do it a third time. 64 slips of paper, take the average, you get 100.11. And you keep doing this again and again and again. And each time, what you're doing is you're plotting this mean on a frequency graph, on a probability distribution. If you keep doing this, let's say 1,000 times, this blue normal curve is what you'll get. You will notice that the mean for your new distribution is the same. It's 100, just like it was 100 up here. So this sampling distribution of means has the mean of 100. But you might also notice that the whatever this funny symbol is, but it's got to be related to standard deviation, is so much lower. It was 16 up here. It's 2 down here. And that's kind of the nature of sampling distribution of means. Now, why did this come out to be normal? Well, actually, IQ scores are known to be normal, right? So as long as your population has something normal, your sampling distribution of means will be normal. But let's pretend for a second we weren't working with something nice and normal like IQ scores. Let's say, just for fun, that this was a bimodal distribution, okay? I would tell you this would still come out normal. Here's why. You took enough samples, like 1,000 samples, and your N for each sample, which has to be the same, was at least 30. So as long as your sample size for each of these samples, and you take enough samples, is 30 or higher, you'll still get this normal distribution. Even if we were working with something else that had a bimodal distribution up here. So that may sound a little confusing. So yeah, we have a question, and then I'm going to show you a video that actually helps a little bit more with this. Why the number 30? Oh, that is a wonderful question. So it's a conventional thing. It's not that at 29 it looks like a completely skewed distribution, and at 30 it suddenly like pop normal. You know, it's not exactly like that, but at 30 it gets normal enough. That's just typically the way it goes. So it is getting more and more and more and more normal at every step, but 30 is like a typical convention number where we say it's gotten normal enough. Okay. So I want to show you this little YouTube video. I hope it's gonna, I actually think I have to change a setting on here where I share the computer sound. Great. And hopefully this will work, and it'll show you this cute little YouTube video. It's about 3.5 minutes long, but it helps explain in another way what I just shared with you. Okay, so I'm going to show it to you. And it's really cutesy, so I'm warning you ahead of time. All right, here we go. Or not. Okay, that did not work out the way I wanted it to. Okay, let me try this again. What I'm going to do now, hopefully, is copy this, since it didn't want to work from here. Share a different screen with you. Sorry, give me 1 second. I should have, let's do this. Share. Yes, share. All right, hopefully this will work. Okay, we're going to have to listen to an ad first, so hang tight.
Verizon knows how to build unlimited right. Start with America's most awarded network. Then, for the first time ever, give families more entertainment with Disney Plus, Hulu, and ESPN Plus, now all included, with plans starting at just $35. The network more people rely on gives you more.
Okay.
Somewhere in the fields, a brave ecologist is studying wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average, and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group, so he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population distribution is not normal to begin with? For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, the more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes, and the closer the mean of the sample gets to the true mean of the population. This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure. There is something very special about the normal distribution. Not only do many things we measure in biology follow a normal distribution, but it also crops up when we look at estimates of variables, even when the variables themselves don't have a normal distribution, as we saw with dragon wings. Because of this, we can use the normal distribution to test ideas about the world even when the underlying variables don't follow a normal distribution. My name is Buthikrit Bhattacharya. This video was created by Shui Cho and brought to you by CreatureCast. Special thanks to Casey Dunn. For more stories, visit creaturecast.org.
Okay. We should be back now. There we go. Okay, so hopefully that was a little bit helpful to you in just understanding the concepts here. So here's the deal. If the shape of the distribution of means will be approximately normal if either the sample size is 30 or greater, like we saw in the case of, it doesn't matter whether the underlying distribution is normal or not normal, or if the underlying distribution of the population of individuals is normal. So in other words, it's an either or situation. As long as you meet one of these criteria, then the shape of the distribution of means will be approximately normal. So in other words, let's say I was starting off with something like IQs. Again, right? We knew that to be normal. I didn't have to pull ends of 64. I could have pulled ends of 9. And I still would have gotten that normal distribution, my sampling distribution of means, because my underlying distribution is normal. So bottom line, this means that the sampling distribution of means will be normal, even if the distribution being sampled is not, as long as the sample size is large enough. And this idea here, as he said in the video, is the central limit theorem. Okay. Yeah, we can go here. I think we're good on. I'm going to break out of here so I can do one more with you. Okay, hopefully this works for me. Hopefully you see this dice thing in front of you, or this random thing in front of you. Oh, we have a question here. Maybe you're not seeing what I'm hoping you're seeing. Let me go to the, sorry, this is all over the place right now. Move you guys back over here. Let me see what the question is. Yes, can we go back over why the standard deviations were different? Yes, let's go back over that. Let's do that. Yeah. Let me go back a few in my slides. So I'm going to go back to the slides for a sec. I'll come back to this. Yeah, that's a good question. So hang tight on this. I'm just going to flip back up here. So this is where we saw the standard deviations were different, right? We had the 16 up here and the 2 here. So what does the 2 versus the 16 imply? The 2 is going to be more narrow, right? That's what they were saying in the video, that when you get a sampling distribution of means, it's going to be more normal and more narrow than the original sampling distribution. So that's why this is such a bigger number than this. In fact, there's actually a formula that that tells you how to get from the main standard deviation to the standard deviation for a sampling distribution of means. So there's something that can actually tell you how to go from one to the other, but that's why it's more narrow. Okay. Now, is there a way I can, let me try this. New share, back to the dice. Okay. Under apps, I may have to change this. Share. New share. It's just popped up in a different window, so I have to make sure you're viewing the right window. Here it is. Okay. Okay, hopefully you all now see this little distribution in front of you that looks rectangular. I am going to throw a die. Actually, what I'm going to do, because I told you that, let me just show it to you this way. See if I already go from 1 die to 2 die, how it immediately starts looking more normal, what that will look like. Now let me increase it. This will only go to 25. I'll go as slow as I can. Well, maybe not. Okay. You see how it keeps getting more normal and more narrow? Okay, that's what we're talking about with the sampling distribution of means. Now, unfortunately, it doesn't go to 30 with this little app here, but that's what would happen. And I'll just show you a quick 1,000 maybe if I run it real quick. It keeps pulling these 25 die, and it's doing it 1,000 times really quick, and it's plotting it each time. So you can kind of see the results, and you see it will eventually kind of get close to what this curve looks like. So you can see how a sampling distribution of means works in real time. There you go. Okay. All right. So let me go back to the slide here. And okay, so there again, you can see the comparison between the distribution for a population, the distribution of means, which is much more normal, much more narrow, and what a little sample looks like on the bottom here, right? That one little sample that's contributing to the distribution of means. Okay, all right. Here we have an example where we have a population distribution of scores. Notice it's normal, right? So we already know our sampling distribution of means is going to be normal regardless of the n. So here we have one that has an n just of 3. And notice here we have one with an n of 9. Same, I'm showing you the same concept again, that it gets more normal, more narrow in that sampling distribution of means, especially more we increase the n. Okay, so it's just the same thing. All right. So here's what I was sharing with you before, and I just want to share this with you about the characteristics of the sampling distribution of means. And I told you could actually figure out how to go from a standard deviation within population to one of the distribution of means. This is how you do it. So what this says is the mean of the sampling distribution of means is the same as the mean. They're equal. So remember we saw before in that other example, it was 100 for the population for the IQ scores and 100 in the sampling distribution of means. That stayed the same mean. Now I'm going to skip down to the standard deviation because that's the most interesting one. If you've heard of standard error of the mean or saw SEM reported in a research article, this is what we're talking about here. So the standard error of the mean, or the standard deviation for the sampling distribution of means, however you like to say that. I prefer standard error of the mean because it's less of a mouthful. What that equals is our standard deviation for the population divided by the square root of the sample size. So you can see the bigger it gets on the bottom, the smaller the whole thing gets. So the bigger the n gets, the smaller our SEM gets. Okay. All right. So now let me say a few words about confidence intervals. This is something I'm sure you've seen out in the literature as well. And basically what we're talking about is a range of values that we can be confident contain the true value of the population mean. Okay. So we have to go back to our concept of obtaining many samples again, okay? So pretend we're going to obtain many, many samples. And pretend that we'll construct confidence intervals for each of them. Whatever that may be, where it's an interval, so it has a high point and a low point. There's the other hand, okay. High point and a low point, and we're going to construct many confidence intervals for, we're going to construct one confidence interval for each of our many samples. 95% of those confidence intervals are going to contain the population mean, which means we can be 95% confident that our interval contains the population mean. So normally at this point, I can't do it very well online, but I'll tell you what I would normally do. I would I'd have a coin, and I'd show people a fair coin, right? Heads and tails. And I would ask people, I'd ask you guys, what's the probability of getting a heads? And you'd probably tell me, well, 0.5 or 50%. I'd say, absolutely, I agree. I would then flip the coin and put my hand over it. And I'd ask you, now what's the probability of a heads? And the most natural response I typically get, and the one I'm sure I would give myself, is 50% or 0.5. But that's where confidence intervals disagree. That's where they get really picky. Because they would say, no, 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 the probability is no longer a thing. This has already been flipped. It exists. Just because we don't know it doesn't mean it doesn't exist. So we don't talk about probability anymore. And that's my long story of probability versus confidence, and why when we're talking about confidence intervals, we want to keep it about confidence. Okay. So the confidence interval for 95% translates to z-scores from negative 1.96 to 1.96. So why is that the case? Okay, so let's explore this a little bit. If you remember our normal curve, remember when we had our two-tailed test and we put 2.5% on each side? What does that 2.5 and 2.5 equal? 5%. 5% from 100, 95%. So really we've got 95% in our center, 5% or 2.5 on each side on our out points. Okay. We could also talk about a 99% confidence interval, same notion. Okay. So now let me show you this picture about confidence intervals. So in this case, we're pretending that there are 20 studies that were run, okay? And the blue line in the center represents the true population mean. So let's take this first study. This black dot's the mean. This pink line, the edges of it are the confidence interval. Notice it crosses the population mean, like most of the time it will, like 95% of the time it will. In fact, 19 of the 20 studies here conveniently cross this blue line. Only 1 of 20, only 5%, do not. So 95% of these studies cross the population mean, include the population mean. 1 does not. If you run 20 studies and do this, that's typically what you'll get. Okay? Most of the time, it will include the true population mean. Every once in a while, it won't. It's kind of fascinating though, isn't it? Like we talked before about this notion of correct and incorrect, and you know, like this is the true population mean. Now this one comes awfully close to hitting it, but a lot of the others don't. So oftentimes we're not perfect in our studies. We try to be as good as we can. We try to do those random sampling techniques. We try to do whatever we can to make sure our sample emulates our population, but doesn't always happen. Okay. All right. This is the typical formula for a 95% confidence interval. Again, I'm just showing it to you. This is something you can derive using SPSS. And what we would do is we have two sides of the confidence interval, right? So that's why we have two formulas here. So we'd start off by getting the square root of n, or square root of our sample size. We would take our standard deviation and divide by that. Remember this? Standard error of the mean. We'd multiply it by 1.96. Remember that number. That's what appeared in our drawing there, where we had 1.96 up and down. That means we got 2.5% on each side. And then we just add or subtract. We add that to the mean or subtract that from the mean. Okay, so that's your 95% confidence interval. So let's pull this together a little bit, everything we've been talking about. let's say we're talking about this post-traumatic checklist that has a mean, a population mean of 30.12 and a sigma or standard deviation of 15 in a non-traumatized general population sample, or general population. We wish to know if people in the community of Moore, Oklahoma will have significantly different scores on the PCL than a sample you'd pull from a general population. So we sample 25 people in Moore, Oklahoma who complete the PCL. We obtain a sample mean of 36. Our alternative hypothesis: people in the community of Moore, Oklahoma will have different PCL scores than the general population. Notice, where did I get that from? Notice it said right up here, different. That's how I knew I wasn't going for higher or lower. I'm just looking for different here. So remember that. That's a two-tailed, non-directional hypothesis. The null, what am I going to add? My not to it. People in the community of Moore, Oklahoma will not have different PCL scores on average than the general population. Now, here's the question. Why do I add that on average? Why am I saying that? Anyone have a sense for it?
Is it because there might be like outliers and stuff that like are way different?
Absolutely right. Yeah, because there might be outliers and stuff that may be quite different. We're just saying on average. We're just comparing means here, really, right? We're not necessarily, not every person do we expect to meet this criteria, just in general. Okay. So we can see this is not a one-tailed test, it's a two-tailed test. That's what we're going to be looking for here, right? Okay. So if we want to actually look at our confidence intervals, we would collect the information from the problem, and we would just fill the pieces in, right? So we would take the square root of n, or the square root of 25. We would take 15 over that 5 on both sides, getting 3. We would multiply the 1.96 times the 3. And then we would either take 36 minus 5.88 or 36 plus 5.88, getting a confidence interval from 30.12 to 41.88. So far, I've went ahead and filled in all of these little numbers from what was up here, what was in the problem, to get that confidence interval. Okay. So what I want to share with you from this is that a confidence interval and a significance test are typically giving you the same information. A confidence interval is telling you, is asking the question, let me put it this way, a confidence interval is asking the question, am I not on the inside? Am I not on the inside? Well, if I'm not on the inside, where am I? The outside, right here in these gray spots. Whereas the significance test asks the much more straightforward question, am I on the outside? If I am on the outside, I'll reject the null. If I am not on the inside, hence I'm on the outside, I'll reject the null. Same conclusion, just different ways of looking at it. Okay. That brings us to our z-test. Now, I'm just going to show you this because I'm trying to make that same point about confidence interval and significance test meaning the same thing. So here, if you notice, this has a lot of the same symbols that we just looked at in the last one. We have the x bar, we have the mu, we have the sigma, we have the square root of n. Remember, this is standard error of the mean, which is this symbol up here. So again, I just fill in my pieces of information. 36 minus 36 x bar minus 30.12 mu over 15 sigma over square root of 25, square root of 25. This again resolves to 5. Square root of 25 resolves to 5. 15 over 5 resolves to 3. And 36 minus 30.12 resolves to 5.88, giving me 1.96. That number should sound familiar again, right? That's our two-tailed cutoff. But unfortunately, we didn't quite make it over the two-tailed cutoff, right? We would have to be just a little higher. 1.965, we would have been there. 1.96001, we would have been there, but not 1.96. Here's our 1.96. Didn't quite make it into the gray range. And if you had looked at the confidence interval, you would have seen the same thing. It wouldn't quite make it into the gray range. It would have been on the inside. Okay. Next topic, and I think we're getting close to the end here, is inferential testing. So we've pretty much gone about as deep as we go with the conceptual stuff and with the kind of like trying to understand the inside versus the outside, the confidence interval versus the significance test. That's kind of a bit of a little bit of a deeper concept, and I think we're getting clear of those, at least for this part. Okay. And we're very excited about inferential testing as well. So let's talk about some takeaways. Okay. We use inferential testing to determine if we believe that we found a significant difference or relationship in our sample that would generalize to the corresponding population. The formulas for the sampling distribution of means are used in inferential test formulas going forward. Now, I did say, and I meant, that we will not be really using a whole bunch of inferential test formulas here. We're mainly going to focus on SPSS, but I am sharing with you, again, so you have that conceptual understanding that this is where it all comes from. Okay, that these formulas in the sampling distribution of means, the ones I showed you for the mean and for the standard error of the means, right? Those all get used going forward. Okay, and confidence intervals and significant tests are high related, as we just talked about. Okay. So at this point, now we can look at we'll look at a z-test one more time. We're once again have the same setup, right? So far, everything's the same. The only thing I've changed is our sample mean. I've now made the sample mean 35.52, and I've specified our alpha is 0.05. So let's look at this. First of all, let me go back up here. Since I said different, I didn't say higher, I didn't say lower, we're talking about a two-tailed test, right? Okay, good. Alternative, people in the community of Moore, Oklahoma will have different PCL scores on average than the general population. The nullest, people in the community of Moore, Oklahoma will not have different PCL scores on average than the general population. Okay. Now, suppose the researcher believes that people in Moore, Oklahoma will have significantly higher scores on the PCL than the general population. Just change it up to one-tailed. Just change this up from different to higher. Okay. Okay. Here's our numbers. Again, this on the bottom is the same as this on the bottom. This is standard error of the mean. This is how you calculate standard error of the mean. So once again, we just fill in our numbers, which are almost the same as last time, except now this is 5.40, and we get 1.8. If this was a two-tailed test, 1.8 doesn't quite cut it, right? It falls over here, a little to the left of our line, a little to the left of the gray area. However, lo and behold, if it was a one-tailed test and we had said a priori it was going to be higher, 1.8 is suddenly in the gray range. Just my way of sharing with you, I think most people really go for two-tailed tests, and that's fine. It is the more conservative way to go. It's less risky. You don't run into that problem of I said it was going to be higher and it came out way lower and now I can't talk about significance, But sometimes you miss out on opportunities, especially if you have low power, if you don't go for that one-tailed test. So it really is something to think about. Okay, just a little bit more for you here, and it's about treatment and control groups. And this relates to the homework you'll be having in some ways. So let me just kind of go through these last few and kind of explain what the idea is. So does classical music enhance plant growth? If that's the question, enhance. So classical music is going to make plant growth be larger than without the classical music. Okay, so here's where if we don't have a control group and we see, lo and behold, the plant did well with music, we don't know what really happened. Would it have done well even without the music, right? So when you just have a treatment group, it doesn't tell you much. Now we're going to add in a control group. Look, it did equally well under the control group condition. So they say treatment had a neutral effect. What would we say? We would say that we're not going to reject the null because it did not significantly increase this as compared to this. Okay. Now, in this case, we finally probably can say we'll probably reject the null because this was in the treatment group significantly larger than this. And finally, another case where we would not reject the null, where we had this actually not doing well with the classical music and this doing well in the control group. Okay, so I just wanted to share that kind of language with you real quick before you attacked the homework this week. That's all I have for you guys. As you can see, if you have any questions for me, if you want to stick around and ask me anything, please feel free. I will go ahead and post those answers for homework 1 for you once we get off, and I'll get this posted up to YouTube as well. Other than that, have a wonderful week. We're going to work on SPSS next time, so if you haven't gotten the software yet, please make sure you get the software and get it installed so we can work on that together next time, okay? Always feel free to drop me a line or check out my office hours. Other than that, have a wonderful week.
Thank